I'm gonna continue to talk about trusses. In other words, how are we going to use a fundamental Newton's law or principles to solve a special case for the rigid body problem? And that special case of the rigid body problems is always called truss structures. Okay, so truss structures are pretty much something like this. And the reason we always use the trusses, and later in the next chapter we talk about beam, is simply because they are cost effective. They are cost effective. Okay, so you really do not need to put a whole bulky materials on the top serving as a roof for the building. That really don't need. So that's why most of the time you see those kind of slender members. Okay, in order to calculate or in the future to design trusses, you need to know how to calculate the internal forces, and then later on you need to know how to calculate the stresses, because these are the basic terms or quantities you have to use to conduct any structural engineering design or engineering design. So that's why, as a first step, you need to know how to calculate internal stresses. Okay? Now the question is, in order to calculate internal stresses, you really have to make additional cut. If you do not cut inside the material, there's no way you can calculate internal forces. Then you may say, well, in the previous chapter, chapter 4, we never do additional internal cut. Because at that time, we're talking about the bulky materials or structures. It's called the rigid body. We are not really designing those things. We'll never design those bulky structures, in fact. Okay? Nobody will do that. It's really not cost effective. So that's why we're talking about real useful stuff, which are always typically like slender members connection or combination. So that's why when we talk about slender member structures, we have to make additional cut. But in general, you need to first look at the entire structure and to calculate the reactions. That is very consistent with what we talk about in chapter 4. So going back to look at the first example again, I was talking about last time, this one. So this is a typical truss structure having all the forces, concentrated forces acting on joint only, in order to satisfy to be a structure, to be a truss structure. So then, typically, the first step, you need to look at the entire structure as the free body diagram. And then you need to calculate those reactions first. That is very consistent with chapter 4. But that's not enough. And then starting from chapter 2, you need to make cuts so that you can calculate the internal forces. And that's why we talk about this example. So in terms of the method of joints, after the first step, calculating all the reactions, we just finished. And then we need to look at joints. And that's called the method of joints. It's really up to us how we're going to pick joints. But the fundamental policy is you need to look at a joint at the very beginning with only 2 members connected to the joint. If you are first looking at some joint with a 3 or with a 4 or with a 3, it doesn't solve the problem. So that's why you have to pick up some joints with only 2 members. For example, like point A or point C. And that should be okay. Okay? So I hope you fully understand the method of joint by looking into this example. And of course, the new assignment was due next Friday. All 6 questions are related with chapter 6. And I think the first 2 are related with this kind of method of joint to solve internal forces for a given truss structure. Okay? Before I move to the second method, which is called the method of sections, I would like to mention something very particularly useful for structural engineering design. And that's this slide. This slide talks about some special cases. Instead of doing the calculations, you can easily identify some members are having 0 forces. If you can identify some members having 0 forces, it's going to make much easier to calculate all other member forces with a given truss structure. For example, if you originally look at this typical truss structure, okay, with very complicated loading conditions, in fact, this is a pin end, and this is a roller support with some kind of forces acting on different joints. Of course, you can just go ahead to calculate the reaction first, and starting from step number 2, you just try to find some joints with two members connected. For example, start from this one and then step by step. It takes much longer time. But in reality, if you know somehow something like these special cases, then you can make this problem calculated in a much easier way. And that's why I want to talk about these some special cases. So most importantly, these are only 2 cases we are frequently encountering, and they are very useful. For those of you in civil engineering, and most likely before you graduate, you're going to take what we call the FE test, what we call EIT test, this engineering training. Of course, the statics is part of the questions you just have to deal with. And many times they just give you these kind of things and asking you what is the force in a certain member or certain members. And frequently, if you're taking advantage of these kind of conclusions, and the problem becomes very easy because they give you tons of questions, probably 100 questions, and let you finish just in probably 3 or 4 hours. You cannot use the 20 minutes to solve each question, okay? But if you look at this one, if you are really trying to solve all the members with this given condition, at least 30 minutes, or maybe even more. Okay, so what I want to talk about among these special structures, number 1 is this one. This is a joint A. Of course, this is a part of the entire truss, okay? But I just focus on this joint, for example. If there are only 2 members, if there are only 2 slender members connected at point A, or joint A, and this angle can be any angle except 180 degree. So this can be 30 degree, can be 90 degree, can be 150 degree, it doesn't matter, as long as it's not 180 degree, because 180 degree is this one, which is different from here. So if this is the case, and there's no external forces acting on this joint A, the conclusion is very easy. The conclusion is both members are having 0 forces. Okay, so it's easy, but it's very significant because we know that if those forces are 0, we don't have to worry about these member forces, in fact, right? So what I'm going to do, I'm going to show you by doing some simple calculation to demonstrate why these 2 members are having 0 forces. So once I demonstrate that, I really want you to understand and to memorize. So this is one of the special cases. After I'm done with this one, then I'm going to move to this one. This is similar, but there are 3 members connected to a point or joint A. And then if 2 of them, any 2 of them, among these 3, any 2 of them are in one line, in other words, the angle between 2 of these members is 180 degree, and then the third one must have 0 force. Must have 0 force. It's called 0 internal force. So I'm going to demonstrate these 2 cases, and then I will extend further for some other cases. So I need to switch to the overhead projector just to show you why we have these kind of conclusions. So I just copy my slides, but without writing any further details. So this is I call case 1. Okay, so at joint A, if there are only 2 members connected to joint A and there's no additional applied forces, and this angle theta can be anything as long as it's not 180 degree. The only exception is 180 degree doesn't work. Any degree, 30, 2 degree, 190, 170, 90, doesn't matter, as long as it's not 180, okay? Then, we use the method joint, in fact, to demonstrate these forces are 0. So, picking up point A, which is here, okay? So, we use a method joint, right? So, we're going to cut this one, which is one of the members called AD. So, we cut this one, we assume, because we don't know FAD is what. So typically we assume there is a force leaving that joint. That's very consistent with what we talked about last time. I called this is FAD. I think this is AD, right? Okay, so I cut in here, that's why I gave a force. And that's the internal force given by this member AD. Also, there's another member called AB. Then I need to cut AB as well. So then what I'm going to have is to have another force that's called FAB. Okay? And there's no other forces. If there's no other forces, this together form a free body diagram. Okay? So this is the free body diagram. Now, I'm going to set up the coordinate system, but this time I'm not going to set up the coordinate system with horizontal vertical direction. If you set up that way, there's nothing wrong. You can finally prove that as well, but it takes longer time. What I'm going to do is I'm going to randomly pick one force direction as x direction. So in other words, this one, it may not be horizontal by the way, okay? So I'm going to say this is my x direction. And if I set up my x direction, then y direction must be perpendicular to this. And this is y direction. Okay, so that's very common. Now, I am going to collect all forces in y direction and set equal 0. Okay, so I'm going to collect all force in y direction and set equal 0. So first off, for FAB does not have any y component. So then FAB should not be involved with the first equation. But we do have FAD. So let's say FAD and multiply with a certain angle. Like call this angle is theta. And I already call it alpha. So the alpha is the angle between this force direction with the y-axis direction. That's alpha. So then, what is the y components of this FAD? That's going to be FAD times cosine, right? Then times cosine alpha. Okay, so this is a y component force due to FAD. And there's no other forces because FAB is perpendicular to y direction because in x direction. There's no other forces. Then this has to be 0. That's fine. Because you only one force, it doesn't matter, negative, positive. But you're right. Okay, so look at this one. No matter what, Newton's law must be satisfied. If Newton's law must be satisfied, if you have A times B equal to 0, then what? Either A equal to 0 or B equal to 0. Okay? There cannot be the third case. So let's say whether this can be equal to 0 now. If cosine alpha equal to 0, then what is alpha? 90 degree, correct? So if alpha equal to 90 degree, then cosine alpha equal to 0. But the question is, if this alpha equal to 90 degree, then what is the angle then? This is going to be 180 degree. But we are not allowing to have this angle equal to 180 degree. That's why we exclude only one special situation, not having theta equal to 180. So if theta equal to 180, then alpha equal to 90. But we do not allow this case. In other words, as long as these two members can be in any direction except 180 degree. So if that's the case, this is impossible to be equal to 0. If this one is impossible to be equal to 0, then the only thing to make this equation satisfy equal to 0 is what? If FAD equal to 0. Okay? So that's why, first of all, by collecting all the forces in this y direction set up equal to 0, you'll find out this FAD equals 0. If FAD equal to 0, then obviously FAB must be equal to 0. Or in other words, you can collect another force equation in x, and then this time you only have FAB, then FAB equals 0 as well. Okay? So we are basically using the method of joins at this joint to demonstrate if there are only two members connected at a certain joint, if there are only two members connected to a certain joint, and the angle is any angle rather than 180 degree, then the conclusion is both members are having 0 forces. Okay, any questions? And that's what's very interesting and very important as well. So this is one scenario I called case 1, which is a special case. And frequently you're going to deal with that. And some of the homework questions you're going to do next week are using these principles or some kind of special cases to easily demonstrate or easily identify where are those 0 force members. Okay, so that's case 1. Now I'm going back to case 2. Well, before I going back to case 2, I need to talk about this case. This is a special case. Having two members connected and the angle happened to be 180 degree. If it happened to be 180 degree, then what? Then of course these two members are not having 0 forces, number 1. But even with this one, these two members are having the same forces. But unfortunately, you cannot say these forces are equal to what? We do not know. You still have to calculate. Okay, so that's why you don't have to worry about this case. Because this is 180 degree, typically you cannot get a very useful conclusion. But this is very, very useful conclusion. This is very useful situation. The conclusion is simply both members are having 0 forces. So that's why I call this case 1. So now for the time being, let's forget about this case. Now let's move back to case 2. Case 2 is another scenario which has 3 members connected to a joint, a general joint A, 3 members. And there's additional condition, which is 2 of them, 2 among those 3 are in one direction. In other words, these 2 members must have the angle between 2 equal to 180 degree. And that's the requirement. If that's the case, then the third one, this is called the third member. That's force. The internal force in the third member, in fact, must be equal to 0. In other words, the third member must have 0 force. Okay, so I can quickly demonstrate why this is the conclusion. Same thing, we use a method of joint. So for case 2, what I need to do at this joint, joint A, I plot the free body diagram. So you have 3 members, right? You cut one of them, and then you indicate there's a force. We don't know the force is tension or compression, then that's fine. We are assuming it is leaving the joint, which is consistent with the tension assumption. What is it called? D, right? So FAD. Okay, so I have one force when I cut member AD, and then I cut member AB as well. So if that's the case, I have another force, which is called FAB. I don't know, it's tension, compression, I assume in tension. That's why it's leaving that joint. And number 3, there's another member. This member, I cut it, I gave another force. This is called FAC. Okay, so this angle must be 180 degrees to satisfy 2 members are in one direction. But the third member, the angle can be anything. The theta can be anything. Can be 2 degrees, 5 degrees, 30, 90, 150. But of course, it shouldn't be 180 because you cannot have 2 members in the same, are duplicating. That's not, you really cannot design that, right? Okay, so now from this free body diagram, we can establish, number 1, the coordinate system. I'm basically just calling this one is x direction. These 2 members in the same direction called x direction. And then the other one perpendicular to this x is called y. So then again, I'm going to observe all the y components of forces in that direction, in y direction, and set to 0, because that's Newton's law again. So now, what are those forces in that direction, y direction? This one does not have y component, and this one does not have y components. The only y components come from FAC. So it's going to have FAC times, again, if you call this angle is alpha. So that's going to be FAC times cosine alpha and equal to 0. Okay? And the negative, again, put a negative here. Okay? Now, same thing. If you A times B equals 0, either A equals 0 or B equals 0. Again, let's check this cosine alpha first. Under which condition cosine alpha equals 0? Alpha equals 90. But going back to look at this one, if alpha equals 90, then what? Then this member should be in the same direction with another member. That's not allowed. It's not allowed. You cannot really make it. So then alpha cannot be 90 degrees. If alpha cannot be 90 degrees, you still have to make sure the Newton's equation is satisfied. So then you have to say, or you have to agree, FAC equals to 0. So what does that mean? That means the third member should have 0 force. Any questions? Okay, so these 2 are very important special cases. And you're going to use quite a bit, in fact. Okay? Just in case, if you want to talk about 4 members, the conclusion is not very useful. But since we have this one, let me just quickly mention this as well. If you have 4 members this time connected to one joint, 4 members connected to one joint, then, and also 2 of them are in one direction, other 2 are in another direction. If that's the case, there's no 0 member forces anyway. However, this member should be should have the same magnitude with another member force, and then this one should have the same magnitude with the other one. Okay, so these 2 should have the same force magnitude. These 2 should have the same magnitude. Okay, and that's very easy to prove. If you set up this x direction, this y direction, you can do that. That's fine. I don't want to talk about too much. Sometimes you do not have 3 members connected, 4 members connected to one point. However, you have 3 members connected, but there is another force acting on this joint, so that two of them in one direction, and then this applied force is in the other direction consistent with the third member. If that's the case, this third member should have the same force and same magnitude with applied load, and also in the opposite direction. That means if this is going down, this is going up. If you have a force going down like a negative 100, let's say going down with 100 pounds, for example, because this is applied load, you must know what is the magnitude. It says 100 pounds going down. Then immediately you know this one. This is 100 pound internal force, but it's going up. Okay, but you still do not know what are these two. You still need to do some other calculations. So that's why I believe these two cases are very, not only popular, as very important. Okay, so let me go back to switch back to my slides, and then based on these two conclusions, let's do some exercise. And of course, the homework number 5 due next week, you have like probably 4 questions asking you to identify what are those member forces. Okay, so again, this is what I call case 1. If you have 2 members connected to one joint, and as long as the angle is not 180 and both are having 0 forces. This one, same thing. You have 3 members connected to a point, connected to a joint, and 2 of them in one direction. The third member, only the third member, should have the 0 force, internal force. Okay, so keep in mind with the 2 conclusions. Now let's look at this general picture. There's a general truss. For this general truss, you just look at all the joints. So first of all, is there any one joint with only 2 members connected to and no applied load? That's probably no, right? I don't see any. That's fine. Let's forget about this one. But let's look at this. You have another case. Because sometimes it depends, right? If the problem doesn't show like this, then you have to forget about this. Okay? Let's look at this case. 3 members connected, 2 of them in one direction, right? So let's check all the joints. Are there some joints with the 3 members connected? There's a lot. First of all, for this one, point F, joint F. Joint F has 3 members connected, right? But you cannot say this equals 0 because the other 2 are not in the same direction. You have to make sure 2 of them are in one direction. So this F doesn't help. But let's look at joint C. Okay, joint C, you have 3 members and 2 of them are in one direction. Look at this. Then immediately you can say that third one is what? That's equals 0. See? So this one equals 0. That's why we use a green line. Okay? Okay, that's good. So that's the conclusion we have based on this. Now, let's go to this point, joint K. So joint K, we have 3 members connected, right? 3 members connected, and then 2 of them in one direction. This one, this and this are in one direction. Then obviously the third one should have 0 force. Okay? Yes?
Why is C 0 if you have the 25 kilonewton applied at B?
You mean point C?
Yeah.
Point C, you are saying why CB is 0, right?
Yes.
Of course, because that's based on this conclusion. Do you agree with this conclusion? I understand what you're trying to say. You say, well, from this point, I couldn't get it. Yeah, of course, you cannot get it. It doesn't mean you cannot get anything from other point. Okay. I'm not talking about this point. I'm talking about this point now, right? So from this joint, certainly this is inconsistent with this one.
Okay, so since now you know that CB is 0,
right,
you assume that the member
it's not assumed. This one, the CB, the FCB equal to 0.
Okay.
It's not assumed anymore, right?
No, but I'm saying since we know that now,
okay,
is BE equal to the 25?
No, they are in different direction. If, let me tell you, it can be correct based on that. Let me just change this example a little bit because obviously this one is not in the same direction with this. So you cannot get, it doesn't satisfy. But let me just tilt a little bit this so-called 25 kilonewton force in this direction. In this direction, okay? Then you are right. Okay. So this BE is having internal force with a magnitude 25 kilonewton. But only the magnitude, by the way, okay? The direction is in the opposite direction. Okay. Okay. Yes?
So you said the green line represents 0?
Yes, because after we get a conclusion, I can put in green.
So with the J to K, or K...
Yeah, we haven't talked about that yet. Yes. So first of all, because the other student was asking this, so I'm coming back here, right? Okay. So number 1, you all agree, right? CB is having 0 force, number 1. And now we move to some other joints. Okay, so now I'm moving this one. Okay, if I move to this one, join K, again, this should be the same with this one, having 3 members connected, 2 of them in one direction. Then the third one is having 0 force. Okay? And you will say, well, wait, that's different because this J is having 4 force. I'm not talking about point J yet. I'm talking about point K or join K. From this join, I have the conclusion. And you can challenge my conclusion, but I already show you using Newton's law to demonstrate that this equals 0. I'm not making any guesses, right? I just basically show you using 2 fundamental Newton equations to get a conclusion. Okay? Now, once this Fjk equal to 0 because of join K, then I'm going to put in green. Okay? Assume you don't know this now. Okay? I haven't talked about this yet. Now, whenever you have this kind of 0 member force, whenever I talk about the free body diagram, it's all related with a force. It doesn't really matter whether you really have a wooden member or steel. It doesn't really matter. So back to this joint J now. You can still say there are 4 members connected to joint J. I fully agree. But the conclusions we got based on these, which called the method of joints, are based on forces. Okay? The reason you have a force or you have a force, of course, this related with the members. I cut a member, I give a force. So now, by looking at joint J, obviously you can say there are 4 members. I agree. But then I'm going to plot or create the free body diagram joint J this time. I cut this one, I give a 1 force. I cut this one, I give 1 force. I cut this one, I give a 1 force. I can also cut JK, but JK's force equals 0. So in other words, in terms of forces acting on joint J, there are only 3 forces. Okay? Because JK, Fjk equals 0. There's a member there, I agree. It's made of wood, for example, right? But it does not contribute to the equilibrium equation because that has to be with the forces. So then what? You're still having 3 forces only, 3 so-called non-zero forces acting on joint J, and 2 of them in one direction. Then the third one is what? Let's go 0. Okay? So do not use the concept we called 4 members at this time because one of the members in fact equal to 0 because of another joint. So then I can conclude Fij should have a 0 force. Okay? So the same thing, this J in fact is kind of 3 members connected in terms of force, right? And then 2 of them in one direction, then the third one must be 0 in terms of force. I'm not saying there's no members. There is still a member made of wood there. But I'm talking about force. The force equals 0. Okay? After this one equals 0, then let's look about joint J. Joint I. Joint I, originally you have 4 members, but one of them equal to 0. Let's say you don't count this one. You have 3 members, right? 3 members, 2 of them in one direction, other 2 with this force in other direction. But this in the same direction, this same direction. Now let me ask you, what is the force in member HI? It's not 0.
20 kilonewtons.
You look at this one, there's applied load. You need to go back to look at this one. So Fhi equal to 20, but that is a magnitude. And the direction is going this way. Okay? And that's 100% true. Although you can say, wow, it's hard to imagine because if I look at this joint H, I really cannot get a conclusion. Of course, if you look at joint H, you cannot get a conclusion. But it doesn't mean if you look at another joint, you can get a simple conclusion. Okay? So, are there any other points? No more. Okay? So, the bottom line is, with a given truss structure, if you take advantage of these 2 special cases, sometimes you can make the problem much simpler. Any questions? Okay, so that's very interesting exercise, in fact, right? So next week, I basically assign you 2 questions. Each question have 2 cases, in fact. You try your best to find out 0 forces without doing the calculation, okay? If you do the calculation, that's a lot of work, in fact. So that's why we only ask you to identify 0 forces with a given truss structure. And typically, these are the 2 cases you can try to apply to solve these special cases. Okay? Any other questions? So this whole thing is within the first method, which is called the method of joints. But in general, method of joints allows you or help you out by calculating all the member forces. Okay? And of course, a certain amount of other problems may not have this special situation. If that's the case, you just have to do step by step. For example, like this. Can you see there are any zero force members? And for this one, there's no. There's no. You have to follow step by step. Okay? And then you may, yes?
So for just because you said like the reason like trusses are made and slender members is because of cost effectiveness.
Mm-hmm.
So what's the point of making a truss with a piece with no force?
Okay, that's a good point. Yes. If that's always the case, you really do not need to add this kind of a member in there because it doesn't have any force in it, right? So it's a waste of material, waste of money. You're right. But let me also tell you, under other loading conditions, because in real structural engineering or civil engineering, when we design structures, okay, sometimes you have only snow load, sometimes you have only traffic load, sometimes you only have dead load, or sometimes you have live load because of like the lighting system, that's a dead load. And sometimes you have the live load because when people walking on the bridge, this is called live load, you have to deal with different kind of load separately. And for certain type of load, you may have this situation. But for other certain type of load, you may not have this situation. So even though for certain type of load, this happens to be zero, it doesn't mean this material, this part of slender member may not be used for other type of load to support to provide the support for the load. Yes, but you are right. If you can guarantee for a given structure, all the loads must be like this. When you do the design, you should not put a member there.
Backup support.
Yes, backup support, that's fine. Yes, right. Just in case you happen to have some kind of even small disturbance.
Yeah.
Yeah, that's true.
External force and another
Right.
part of it becomes
That's
braced.
right.
And
Yeah, that's good. That's a good point. In other words, I can tell you this. For example, let me look at one of the. No, I just use this one. You see here, I did not plot the reaction, the support. This point A is a pin end. That's why you have two reactions. Okay. This point L is a roller or a rocker. That's why you only have this reaction, right? But let's say if all the force, just in case all the force in y direction, then the question people would ask you is why you are designing a pin at a joint A instead of putting another roller. Because if there's no horizontal forces, this one is guaranteed to be zero, right? But only for that case. But sometimes when you have a small disturbance, it's small wind, if you do not have any resistance in x direction, then this structure will fly. Okay? So that's why you have to prevent from such unpredictable cases. Okay? So thank you. You're right. Back up. Okay, so this is the method. It's called the method of joints. Okay? Method of joints allows you to calculate all member forces. So if you were given a structural truss problem asking you to calculate all member forces, you don't have a choice. You just have to use a method of joints. Method of joints allows you to calculate all member forces.